In this lecture, we're going to focus on image formation again, but this time what we're going to do is look at the kind of pipeline model that is used in most graphic systems, and certainly all of the interactive real-time systems, and in particular, it's how we get the OpenGL architecture. So what we're going to do is look again at the process of image formation and look at how that goes into the design of an actual graphic system, which will be a pipeline kind of system, and then look at what each of the stages in the pipeline have to do. And finally, at the end of this, we'll say, okay, now we have the pipeline architecture that looks like this with the various processors in the pipeline. Now, what does the software interface to that look like? What kind of functions are going to be in an application programming interface or an API, in particular in WebGL? So let's go back to image formation and to the argument we were making in the last lecture, which says, okay, what we did in that is we talked about image formation, and we said we want to have independent specifications of the objects, the materials, the viewer, the lights, all the things that we need to put together to get an image or what goes into a scene. And this is the kind of the physics point of view where all of these things are independent of each other, and it's the job of the implementation to put that all together. But in terms of the application programmer interface, we'll expect to see separate functions for each of those items to specify the objects, to specify the materials, the viewer, the lights, and so on. But then how later we'll get, in the next lectures, we'll get into the actual implementation of that. But to go back to the original physical approach, we started with this idea of a ray tracer, and let's just go back over that for a minute or two because we're not going to come back to this until really the end of the course, is that we follow rays of light from the center of projection through an image plane, which we've now put in front of the center of projection, and it's ruled into pixel size little squares or rectangles, and we follow those rays and see what happens to them. Now, the advantage of this approach is that we can handle, at least in principle, any physical effect, because we're going to follow the ray, we'll see what it does, whether it gets reflected, scattered, transmitted, absorbed. We can check each one, we can handle in principle, at least, multiple reflections. Ray tracers love to have images of a lot of glass balls where the rays are bouncing from ball to ball, and they can handle that kind of thing, and they can handle translucent objects. The problems are that it's slow to carry out all of these kinds of intersections, because in order to trace a ray, it could potentially intersect any object you don't know in advance. So what a simple ray tracer would do would say, well, let's start with the first pixel up here and let's shoot a ray through it, and then we'll see what happens. Well, I don't know what happens in advance, and I'm going to have to see how it might intersect every object. So the whole database of objects must be accessible all the time, because you don't know what's going to happen. So that sort of makes it a slow approach. It can be memory intensive depending on how many objects you are and what kinds of objects they are. Now, another approach we'll look at, and there are a couple of variants of this we'll see at the end, is called radiosity, where it says, well, why don't we look at this again in a physical point of view, but more of an energy balance point of view, so that if we look at what's happening in a room with light sources are putting out energy. That energy is going around the room, it's absorbed by some surfaces, it's reflected by others, and in the end we have an energy balance, and we could try and find that energy balance. And the radiosity approach is something that actually came from thermodynamics, which was trying to do the same thing, but it's very, very slow, but has some usefulness for certain kinds of problems. And then there's a number of approaches that are in the middle that we'll hopefully have time to survey at the end of the class. But what we want to do is take a much more practical approach and say, look, we're going to do things and we're going to process them in terms of objects. So I'm going to take one object, a triangle, a quadrilateral, maybe some more complex object, and I'm going to process it one at a time in my application program, and that application program's job is going to be to output the vertices for that that define that object. We're making an assumption here that I can choose a bunch of points in space that will define that object. So if it's something really simple like a triangle, I'm talking about 3 vertices. If it's a cube, I can talk about 8 vertices, and so on. And if I'm talking about curves, I can use the vertices to define various types of curves and surfaces that we'll discuss later in the class. So the pipeline architecture takes those vertices and puts it into a vertex processor. Now, that vertex processor is the first shader. It's the vertex shader, and it takes in vertices, and it will actually output vertices. And we'll talk a little more about what goes on in this box in a minute, but let me go over the whole thing. So after the vertices are processed, they go into a piece of hardware. And all of this stuff lives on the graphics card. And primarily, if it's good GPU, this is all inside of the GPU. So the vertices come from the application program, and one way to look at this is the primary job of the application program is to produce a bunch of vertices that are stuck into this pipeline, and then they flow down the pipeline until finally they come out the end as pixels, which are put up on the display. So the vertex processor does a bunch of jobs to those vertices I'll go over in a second. It then passes it on to what's called a clipper and a primitive assembly, which you might look at as something that occurs just after that or as part of vertex processing. But the idea is that what the vertex shader will do is done on a vertex by vertex basis, and it doesn't know anything about objects or anything bigger. So if you send 3 vertices for a triangle, it's going to process each one independently and have no idea that it's a triangle. But at some point you now right after that have to put things together and say, oh, these 3 vertices are a triangle, or these 3 vertices are simply 3 points, or if it's 4 vertices, whether it's 2 triangles or 4 points or a quadrilateral. And that's what the idea of primitive assembly. It's putting all of that together and then deciding, the clipper is going to do is decide if that object that's been defined and processed by the vertex shader actually is visible. So this is where some of the viewing comes in. It says, okay, these objects can't be seen, so we're going to discard them, and these other ones can be seen, and so I'm going to pass them on to the rasterizer. Now, the job of the rasterizer is to take vertices. What comes out of this is still going to be vertices, and to take those vertices and knowing what objects they define, and decide which possible pixels are affected. Think of what we call a fragment as a potential pixel. I may not be sure that it's visible. It may be hidden by something else. I may go through a later process that throws it away, but at least it's potentially visible on the display. And what I have to do from those vertices that come in is decide which pixels could potentially appear from that object. So again, think of this triangle passing through. I decide here that it's visible. I pass on those 3 vertices, and now if it's filled the way we often deal with triangles, we don't display their edges. We tend to fill them with a solid color or pattern or some more complex shading, but something has to generate the locations of all of those fragments or pixels, and that's the job of the rasterizer. It does a few more things we'll talk about later, but its primary job is to produce fragments, and those fragments go into a fragment processor, which can further process the fragments coming in. So you may have a limited number of vertices coming in, but lots and lots of fragments being processed over here, and we'll talk about those jobs in the next couple of slides. Okay, so let's go start with the vertex processor and look what its jobs it has to do. It starts off where its main job is to process vertex location information. It may also process other information that comes along with that vertex, like colors, but its main job always is to process those locations. Now, its primary job is to put everything in a coordinate system that the next stage understands. And we'll go through these coordinate systems in more detail, but a very brief overview is that we'll start by specifying our objects in whatever system is best for our particular problem. And that's one of the nice things about computer graphics. We're not stuck with some set of units that has nothing to do with the problem we're working on. So I get to pick the units I want. Those will be called object coordinates. There may be a stage preceding that where we do the modeling, but let's say we form an image in the world with a bunch of vertices that specify objects, and their locations are given in object coordinates. Now, what we want at the end is what the camera sees, what the viewer sees. And so there's going to be a transformation that goes from object coordinates to camera coordinates, and that's one of the things that the vertex processor or the vertex shader has to do, is make that transformation. It's also going to make another transformation we'll talk about in a second. But no, at the end though, we don't care about those units over here. What we care about is locations on the display. Where are those pixels? And so there's going to be some other changes in coordinate systems here. And eventually we want to wind up in something called screen or window coordinates, which are in units of the pixels. Generally, they're integer units of how many pixels from the top left corner or the bottom left corner that pixel is located. And the other things that this vertex processor can do, the most important one, is to compute a color for each vertex and send that along with the vertex. We don't have to define colors there, but generally that's the most obvious place to do it. It's the one that's used the most. So with each vertex, there's an attribute called its color, and if that color needs to be processed, for example, for example, getting that color as a result of some lighting and shading calculation, we can do that in the vertex processor and send it on. Now, the next step is the projection. That's the process we saw when we looked at our model of imaging for a human viewer or camera. There was this projection process that started with these three-dimensional objects, and then we had a viewer or a camera. We drew that bellows camera that exists in 3D, and then we produced, by tracing these projectors, a two-dimensional image. Okay, whether it was a parallel projection or a perspective projection, that's in a way conceptually simpler because it goes right through a center of projection. The parallel projection, all the projections are in the parallel to each other, so we have a direction of projection instead of a center of projection. But that step is also done as part of this vertex processing before it gets to the rasterizer, because we're going to go from 3D, and eventually the rasterizer is going to work in 2 dimensions, and we'll see that later. But so what goes on here is changes of coordinate systems, one of which also occurs as part of the projection process, and puts things in a coordinate system called clip coordinates, which the rasterizer can use. Okay, primitive assembly we've talked about. We'll be talking about assembling just for line segments. So if I have 2 vertices that specify a line segment, the rasterizer has to generate, say, hey, well, first the primitive assemblies has to say that's a line segment, and I'm going to eventually get all of the pixels that are along that line segment, the same polygons. Generally, I want what's inside. We'll talk about curves and surfaces later. Same idea, we have to produce the fragments and know what they are, but that'll occur a little bit later. Okay, clipping, we've said that's the process of saying everything that's not visible I'm going to throw away, and I don't have to rasterize that. So I want to do that before I get to the rasterizer, so I don't waste that work and generate a lot of extra fragments. So here's the view going back to that synthetic camera model, and says, look, everything outside of this field of view or angle of view I'm not going to see, and that process goes on automatically within the GPU. One thing that's a little different from viewing in the real world is that in computer graphics we can call these things the top and the bottom clipping triangle here. If it's a rectangle, if it's a parallel, or parallel pipette if it's a parallel view. But also what we do in computer graphics is we have a front clipping plane and a back clipping plane. which is, generally if you think of this as a camera of the eye, we think of it as seeing everything out to infinity and in front of it. We don't do that in computer graphics. We have a front clipping plane and back clipping plane. So the things that we see are inside of this truncated pyramid, which is called a frustum, where you just cut off the tip. And the job of the clipper is to find out what's inside of here and throw everything away that's outside. Rasterization, as we've said, produces these potential pixels, and so what comes out of the rasterizer is this flow of pixels to be processed. A lot of parallelism in the GPU, so there are many fragment processors that can be going on at the same time. But what the information that comes out is the location has to come out. So what comes out of this is a potential pixel with a location in the frame buffer, and it may have a color, which is the color that we set back up here, which will be averaged over the primitive here as part of the rasterization, and other information may come through. So even though we've done projection here, some of the information about depth will be carried on through this process and available to the fragment shader inside of the fragment processor. So remember again, in WebGL, you have to write both the vertex shader and the fragment shader. In the older versions of OpenGL, the functionality, and it was based on the same pipeline, but the functionality was fixed. You didn't have much control over these operations. Now it's totally up to you. You must load the code in here, and you must load the code in here. Okay, what can you do with a fragment processor? Well, its main job is to finalize that color of the pixel, and also it may do some determination of whether that pixel is visible or not through some hidden surface removal. Whether something is visible, if something is in front of it which is opaque, I won't see it, and that is handled somewhere along the line by a hidden surface removal process that actually occurs a little after this, but we'll talk about that later in the class, actually fairly soon, because we're going to need that. Or if we have textures determining the color, so we're trying to, say, paint an image onto the surface of an object, a simple object that we've defined, say a rectangle, and we want to paint an image on it, that's a texture map, and that occurs in the fragment processor. So actually, if we wanted to make this diagram a little more complex, this would be the pipeline that the geometry flows through, but images that we want to use as part of the forming the colors for our objects would come in here. So a texture image would join at the end here during fragment processing and be used to either totally or partially determine the color of the fragments that went out. Okay, now let's turn to the programmer's interface for a minute or two and see, well, what do we need? Well, let's back off a little bit and say, okay, here's the hardware we've been talking about, and the GPU is in here, and I'm going to write an applications program that's going to do all of the things that I just talked about. How do I do it? Well, I'm going to do it through an application programming interface or API, and that's very simply, it's our graphics library. And so what's going to go into that graphics library? Well, we've talked about this a little bit, but let's look at it again briefly. So we got to specify, as we've seen, the objects, where the camera or the viewer is. If we're going to do lighting, we have to say something about what kind of light sources and where they are, and what kind of materials are objects composed of, so that we can apply some sort of model for how things reflect. For now, we'll leave aside input, although in about next week probably we'll start talking about input from the mouse and the keyboard, and we may want to have some idea of the capability of the system. I say that because one of the things that we're doing here, and this is the trend, been the trend for a while in computer graphics, is to talk about what's called device-independent graphics, where you write your programs, and your programs in principle don't have to know anything about what kind of particular hardware you have, what kind of display, what's the resolution of the display, do you have a mouse or do you have a trackball? Any of those things shouldn't matter when you're writing a program. On the other hand, if you want to get really high resolution, say photorealistic images, you'd like to, if you're going to do all that work, you'd kind of like to know what the capabilities of the system are. Does it have enough resolution? Can it produce enough colors to make that look realistic? If it doesn't have this capability, I'll do something else. So there's some things about the system that you may want to know, and there may be functions within the API that let you query or ask the system what are its capabilities. Okay, what kind of objects? All objects that we're going to deal with are going to be specified by vertices or locations in space, and we're going to be dealing with 0, 1, and 2-dimensional objects. Now, what do I mean by that? The dimension of an object is sort of how many independent directions you can measure on it. So a point is just a location in space that might get displayed as one pixel, but it has no width or height or depth, and so we can call that a 0-dimensional object. A line segment, well, that's an easy one. You have length, but you don't have width. An idealized line segment has no width, but it does have length, although we must display it by giving it a little width, or else we wouldn't see it. But that's a 1-dimensional object. A polygon is a 2-dimensional object. It lives in a plane, hopefully, and it has well, let's say any object that's a surface is a two-dimensional object. And then we can go up to a 3-dimensional object, something like if we were working with a cube as one of our basic objects, that would be a 3-dimensional object because it has height and depth and width. Now, how do we specify these within the API? Well, here's my one little slide of old OpenGL and how we used to do things. And it was actually simpler before in some ways, because we'd say, look, here's a function, GL begin. These were written in C. And it says, here's the beginning of a polygon. This says, okay, so it begins an object, gives it the type of an object by some defined constant, which is we call GL polygon. Then we can give it the location of the vertices. So we say, okay, here's the first vertex. It's a 3-dimensional vertex. I'm going to give you its values as floating point numbers, so it's at 0, 0, 0. Likewise for the second vertex and the third vertex. And then you say, well, I'm finished with that. It's just a triangle, so I use the function gln. That's it. And what would happen in an older system is pre-shader-based systems is this would simply be the definition, and it would flow right through the system. In fact, as soon as you define this vertex, it would go flowing down the pipeline. This one, and GLN would say, okay, that's for primitive assembly. This is now I can assemble these into an object, but it's what's called immediate mode graphics, which we'll come back to. Now, we don't do that anymore because for a lot of reasons we're going to be seeing, because it's much, much more powerful to use the GPU. This doesn't really make full use of the capability of any modern graphics system. So this has all been deprecated. These functions do not exist in WebGL anymore, and they've been removed on modern versions of desktop OpenGL. So here's sort of the beginning of a GPU kind of example for the same thing. And the first part is easy. Well, if you want that same triangle, I'll just put it in an array. So here's JavaScript says, okay, I'll have a JavaScript array. I'll put in 3 points. In our library that we're going to use in this class, we have a vec3 type in there, which makes it a lot easier because it corresponds to things that are in the shader. But if you wanted, this could just be a 3-element JavaScript array and another 3-element JavaScript array. At this point, that's not crucial, but the idea is that this is formed and nothing yet is happening with it. We've specified our geometry by putting in an array. We might have had a bunch of code that defined those values by some other process or altered these values, but then as a separate step, we're going to send it to the GPU. What happened in this example is, as soon as I defined that vertex, off it went to the GPU. As soon as I specified this vertex, off it went to the GPU. Here, nothing is going to the GPU when I define my data. A separate step is required to send that data to the GPU. And as we'll see in the next couple of lectures, you have to form a buffer on the GPU and then put these data into that buffer. Now, still, I'm not going to see anything because there's a third step, which is very simple. I tell the GPU, you now render that data that I put in that buffer. So it's kind of a 3 or 4 step process. The fourth step would be, well, what about the shaders? And I haven't talked to you about how we define our shaders. That'll be in the next couple of lectures too. But it's a very different process. This is called, by the way, retain mode graphics, where we keep this information. Notice that once I put this information onto the GPU, it's going to stay there. So if I want to reuse it or redisplay, it's there. In the immediate mode model, one of its big weaknesses is this flowed through the system. Maybe this triangle appeared on the display if it wasn't clipped, but it's now gone. There's no memory of it. Immediate mode means really immediate. It's gone. It's not stored. So retain mode says, hey, that stuff is already there. All that data is there, and you could do other things with it. Even just simply say move it around the triangle around the display. Okay, now the camera. Let's go move on and talk just about 1 or 2 other things. What about specifying the camera? Well, you're going to have to figure out how to do that. Well, I'm going to tell you how to do it. You don't have to figure it out. But there are a lot of ways to do it. Because the camera specifications are usually inside of the vertex shader, there are many ways to do it. If you think about how you might want to do it, we can argue this way. Here's a little bellows camera model. How would we say everything we need to know about that to specify this image? You know, equivalently, when you take a picture with your digital camera and all this camera information gets sent back to your computer when you upload what kind of information is it? Well, what was the position of that camera? Well, it turns out that's a 6 degree or a 6 variable problem. You can say where the center of that camera is, the center of projection, the center of the lens. That's 3 variables, but I can twist it about these 3 axes. If I place a camera coordinate system at that center of projection, I can independently twist the camera in 3 independent directions, the kind of thing you can do with a tripod, say. You can rotate the camera in those 3 directions. So it becomes a 6-dimensional problem. I also have to specify the lens. I could put a wide-angle lens in, a telephoto lens in there. I also may want to say, if this is a camera, a good camera with some flexibility, I have to say, well, how big is the back of the camera or the back of the film? Because that's going to determine how much of what comes in here for any lens and any orientation I actually see. So the film size is another specification we would have to make. And if it was truly a good camera, or like an old bellows camera and some architectural cameras, you could move the back relative to the front. Most of the cameras we use, whether they're single lens reflex or just your phone or something, the back of the camera is always parallel to the front of the camera, and we can't change that. One of the nice things about a bellows camera, because this is flexible, is we can have almost any orientation between the front plane and the back plane, which allows us to create different kinds of images, and that will give us a lot more flexibility. We'll see some of that in a couple of weeks when we talk about camera specifications, whether we have functions that can do that. For lights and materials, we're going to mostly talk about, when we get to this part in a few weeks, talk about point sources. You can have a distributed source like a real light, but we'll deal realistically in our APIs primarily with point sources and variants of that. A light spotlight is sort of like a point source. A point source goes equally in all directions, and a spotlight just takes a part of that. Near and far sources are just ways of saying if you move a light really far away, the calculation becomes much simpler. For example, if you think of the sun, it doesn't really matter how that if I'm standing behind you, that I'm further from the sun than you are. The distance is essentially the same, and we can take advantage of that in our rendering algorithms. Obviously, sources have colors. We'll talk about the color properties. And material properties kind of match the light properties. For every color here, we'll have a matching color property for a material, but we'll also have to talk about how much of the light is absorbed by the material, and for the light that's reflected, is it reflected equally in all directions, which we said was a diffuse surface, or is it concentrated in one direction like would be the case with a mirror. So these are the functions we expect to see in our API. Some of them are, almost all of these were in the older OpenGLs with the fixed function pipeline. What we'll see is that you can either write your own, or we've created a matrix vector package that goes along with this course that has a lot of that functionality in it, so you'll be able to do a lot of light material calculations without having to create everything all over by yourselves. And we'll see this all over the next few lectures.